All right, thanks for coming or listening online to the second section that I've done. And today, just going to recap what you learned. So I'll do a recap of things because now the class is going to be divided and start to move in a different direction like I've been kind of suggesting. So let me review what you've basically done. Basically, Yvonne in the class has done an overview of frequentist methods, and in those methods you derived quite a few estimators. One of them, for instance, is the LS estimator, the OLS estimator, the least squares estimator, and this is how you compute that estimator and use it. X transpose X inverse X transpose Y. This estimator can have problems like when you have heteroscedasticity. So when you have heteroscedasticity, you use a different estimator, which we also derived. And that was given by an equation that's in your notes. And the GLS estimator is the solution for the heteroscedasticity problem in the least squares estimator case, and you use it to get back to the best linear unbiased estimator. Okay, so you want to restore your best property, which you lost when you have heteroscedasticity in the least squares case. Not feasible though, because you don't know what omega is. Unless omega is known. So it's usually not known. So you'll use the FGLS estimator, okay, which is also somewhere in your notes. But to get it, there was an interesting couple of steps that you needed to do, like estimate omega is replaced with this omega hat, and omega hat is estimated by another regression. You estimate these with some function like log, which gives you like an estimate of the powers that could be influencing the z's. So that's how you get these e hats, and then you form omega hat with the results, the fitted values from this regression. And that's how you do it. So after that, you form the FGLS estimator, use that to run least squares. Okay? And we also did the ML estimator, which is also similar to the least squares estimator. But the one difference is that the estimate for sigma squared happens to be biased. So just be aware of that. And you get it by maximizing the log likelihood function. And that was like the homework problem that Yvonne wanted you to check out. And there's a link on the canvas where you can see the problem statement, and you can try it yourself. But this is in a lot of books. So one thing to note is that these estimators have been derived for their useful properties in finite samples. Those properties are that it is meets the Gauss-Markov theorem. They're the best linear unbiased estimators. In what sense of the word are they best? In terms of efficiency, right? And we're restricted to just linear and unbiased estimators. Okay. Well, one thing you may be asking yourselves is why linear and why unbiased? Why those two things? And one of the reasons why we are only considering linear and unbiased estimators is that the estimators are evaluated based on the cost function. Okay? It's not really important for you to know this, but it helps motivate why we're doing Bayesian statistics now. A cost function is basically how close an estimator is to the true value. And the most commonly used cost function is, let me erase this. The most commonly used cost function is this one, which you'll recognize. Okay, so it's just the mean squared error. Okay, mean squared error just penalizes it by the square term. Penalizes the difference between theta hat and theta by this squared. And you average over that, and you get an expectation of the cost, and that gives you some idea of how good one estimator is in comparison with another. Well, one of the reasons that we're only considering linear and unbiased estimators is that because if you were to take these restrictions off, there's many estimators that are better in terms of cost, which is a good thing. You want things to have the lowest cost possible. They would have better costs, but they're not linear and they're not unbiased. Just restrict everything just to this. Okay, so just only look at these, and then you can derive it, because obviously if you minimize this, you'll get the least squared estimator. So just restrict it to these, and then no problems emerge. But if you were to take it off, there's estimators that actually do better in some circumstances than the linear unbiased estimators that we're only looking at. If you just do the frequentist way, the Bayesian approach does not average over stuff that you've never observed before. But it assumes, one of the things, assumes that parameters are now random. Oops, I spelled that wrong. So you have to specify some sort of degree of belief about what the way theta is distributed. It could be a normal distribution, like the frequentist setup, where you have, a error term that's given some certain distribution which gives structure to the y. You have to assume a data generating process. So, like frequentist, you assume a data generating process. Assume some DGP. Okay, so that would be the likelihood function. Okay, and the goal is to derive a distribution for your parameters that's been conditioned on what you've already seen. This conditional distribution is what you want. You like to know what is, how is theta now generated that I've observed y and seen it? What is this distribution going to be? Well, if you think about just conditional probability, this would be the joint distribution of y and theta divided by f of y. Except that usually, I don't know, for whatever reason, I just call this my. So I'll call that m. So this joint distribution is going to be some combination of these two things. And that's what we did in class. So that basically gives you the background of why we're doing this. You'd like to you're after this posterior distribution here. And to do that, you first need this numerator. So drive this. Let's see, what's one way to do this? You have this joint distribution, but this is also equivalent to this one. Okay. Just by conditional probability rules, you could get this. So then use that above, and you have like the basic Bayesian formula. And this is it. Okay, so a lot of the problems that we'll do, you'll start off by mixing these two distributions and deriving this. Okay, right now I'm going to try to show you how to do the problem, second practice problem that I put up. And I'm going to start from somewhere that I've already done with some other students, but I put this online, and this is the notes that I have for the very first problem. So the next problem that I have on there is deriving a marginal distribution of just beta, marginal of sigma. And so from working from what's in the box right there, I'm going to try to do that. So let's see here. Let me show you basically what we've got. This is where I got last time, and you can check online and get the notes. But we're going to define updated parameters. Okay, so like this one, for instance, I'll call this gamma 1. And then the other new parameter that I'm going to define is this one. And that'll be delta 1. And that'll make it easier since I won't have to drag around so many parameters. And this is my summary of why we did everything in problem 1 that we did. So you can see here that this is in the form of like a normal distribution, and for sigma squared you have something that's like a inverse gamma distribution with new parameters gamma 1 and delta 1. Okay, so that's what this says. Now we're going to want to integrate out some of these parameters, because here is what we ended up with as a result. We ended up with a joint distribution of beta and sigma squared. But what if we want just one of the marginal distributions of either beta or of sigma squared? Okay, so I'm going to save this right now and open up a new project so I can show you what I'm going to do. Okay. So now I have some blank notes. So on the question that I put up online, I can show you too on here. Let me open the first section. This is the first section. Go down to the last question. These are, sorry, not the last question, but the second question. Here's the first question. This was deriving the joint distribution. The second question is deriving one of the marginals. And there we go. This is the problem statement. Now we're going to derive the marginal distribution of beta, not conditional on sigma squared, marginal of sigma squared. And then we want to show that the resulting posterior is t, is a t distribution. And we can also show that we've got an inverse gamma distribution for sigma squared. Okay, so those are the two things that we should do. So let me give you my hints there. I'll close this one. Now that you know what the question is. And start a new one. Okay, so I showed you that in the end, or you're going to show that you get a t distribution when you're all done with this. Okay, you'll have some new degrees of freedom. Okay, well, let's just leave it like that. So t distribution has this PDF. I'll write it out for you. Kind of complicated, but this is where we want to end up when we're done. And since I'm giving you problems in the scalar case, this is just the univariate t. I'm going to do multivariate in a second. I can maybe next time I'll show you multivariate. So this is a t distribution. So I'll just write this out real quick. This is where we want to end up. We want to get to this point after integrating out sigma squared. Okay, so the goal of practice problem 2 is to integrate out, you have this joint distribution of everything. You want to integrate out sigma squared, okay, over its support. like that. And that will leave us with a marginal distribution for beta, given y. Okay, so remember, definition here of marginal is a marginal. This is the equation for the marginal PDF of something. All right, so that's what we're going to do. We're going to derive the marginal distribution for beta. Doing that, we'll integrate out sigma squared. You can see the parallel between these two very clearly. And we're going to start from that large equation that I showed you before. And I'll have to copy that and bring that over here because I don't want to write it out. So let me save this one. Then I'm going to open open this. I'll just take everything that's here. See if I can do this. Yeah. Okay, now with this, I'm going to refactor everything so that I can integrate it easily. Because you can see I kind of have a inverse gamma distribution already. New parameters I want to define though. Okay, make it easier for me. So let's do that. So, well, maybe I don't want it to, everything to disappear. Down here, rewrite just a little bit this stuff. Okay, so I got something like this. -1 and this one. The exponential terms. One and the other one. Okay. Define a few. Well, no, I don't need to. This one is this parameter is defined elsewhere. And I think everything else is self-explanatory here. Okay, so what I've written is now proportional to this marginal. All right, so I'm going to combine these two. Yep. Okay, that's those two combined. Combine these two. And this. Okay, so those two are combined. And that's proportional to the marginal. All right, so again, the goal was to integrate over sigma squared to get a marginal for our beta, given y. So do that using the PDF trick. and you're going to use this trick again and again in this class. Alright, so the PDF trick, basically what we have here is a new inverse gamma with this new parameter and this new parameter. That's an inverse gamma distribution. So I know that the integral of this is going to integrate to this one here, beta minus beta hat square, okay, to the delta over 2 negative sign, and then over some other stuff, but since we're doing up to a constant of proportionality, those normalizing constants don't matter to me. And the reason why those constants of proportionality don't matter is just simply this. I just want a posterior distribution. So if this is my normalized posterior, and this is my unnormalized posterior, then if I take the, let's say this is like x and this is y. If I take the expectation of a normalized one, I get mu. If I take the expectation of the unnormalized one, I still get mu. Okay, it's still in the middle. Even though it doesn't integrate to 1, it's still right in the middle. So my point estimates will still be just what I want them to be. I just want to integrate to 1. So it doesn't matter what these normalizing constants are. Because if you look at the inverse gamma distribution, you would realize that there's this gamma term. Let's see, what would be in there? This one. This one. To the minus 1. But we don't need that. Okay, you don't even have to worry about that because it's just up to a constant of proportionality. This is the kernel. This is the kernel of a t distribution, so it's really all that I need to look at. I'm going to do a new page now. So let me copy this. Oop. Okay. Now I just need to rearrange things because you see here in the t distribution, to compare what we have here, I'll just make this real small. Okay, so this is what I'm comparing it to. I want the degrees of freedom are right here, they're new. So this is a t with new degrees of freedom. So t with new degrees of freedom, this is the degrees of freedom. I need a degrees of freedom parameter there and a 1 here. And then this stuff, this is the constant. Okay, I don't care about it. I just care about the kernel. And that's what I have here, basically. So I can divide by gamma 1. Like that. And that's what I'm going to get. So this gives me 1. And then I need the degrees of freedom there. This is not the degrees of freedom, this is 1. So I need a 1 over delta 1 here. So I multiply by delta over 1. And yeah, 1. So pretty much done. Just make a few adjustments to this. It's probably better. Alright, so that's a t distribution now. Clearly it's a t because it's like this. Okay. And this is distributed t. And now I'm going to specify all the parameters here. You have delta 1, degrees of freedom. This is a non-central t, so you need to center it. Mean beta hat. And it has this shape. Variance parameter, third parameter, phi squared, like this. Okay, so this is what the goal of the next problem was. What this means practically is that you, if you were interested in knowing more about beta, knowing a point estimate, getting some idea of what the average value of beta was, you could use its distribution to compute its moments. Okay, so its mean would be here, so a good guess of its mean would be this parameter. You can compute it. You could compute an interval estimate using the variance and things that you know about the t. So that's what the goal of this problem was. It's one of the last problems that you'll be able to do this, where you'll be able to actually integrate out the other parameters easily and come up with marginal distributions for the priors. Let me show you the other one. If you look here, you have this stuff. So let me copy that again, because we need that. I have to drag it down this way, or else it doesn't work. I'll drag this to where I want it. Alright, so the other prior distribution is sigma squared. So it's proportional to this distribution. So right away I can just, oh wait, no, I can't do that. I can't get rid of this one because that has a sigma squared in it. This has a sigma squared in it. So need to look at what I have for sigma. I need to actually combine everything. Okay, so again, this is delta 1. Delta 1 over 2 minus 1. And then this one. So actually, should combine these two. Okay, so this is a new parameter. And then here we're going to have some other stuff. This is gamma 1. And all this. Squared. All right, and this is proportional to an inverse gamma distribution. So Alright, that doesn't look like a gamma. Let me do it again. Okay, and again, if I wanted to get some estimates of sigma squared, I could use the mean of the inverse gamma distribution, which you can look up. I don't know what it is. But that's what you could do with it. And you could also come up with interval estimates and such things like that. Credible intervals. So this is what that distribution will look like. So it was pretty much already done for you in that question. And those are the two things that you'll need to do. Now, if I change this question a little bit, the reason why you could do this and why this question was simpler, I guess in some ways, because you can get known distributions, was because of the way that I specified the prior. The way I specified the prior in this question was I gave you prior for beta that was conditional on sigma squared. Okay, so that was the critical assumption here. That it let us do everything nicely. And a prior for sigma squared. And then you had the likelihood. Now, if I didn't do that, had not done that, I specified my priors this way, and I still would have been able to get, you know, I still would have been able to write this all down and get a joint distribution for the data given the parameters, like this. Okay, this would have been the beginning of the problem, but notice this is different because my prior is different. And this would have been proportional to this. Okay, but if I had done it this way, everything would be different. And you can try that if you want to. But because I've specified the priors differently, I'm not able to get marginals for these. Okay, so if you do this, you can't get marginals. Marginals analytically. Like we just did. You'll need to use the MC methods. Okay, so the MC methods are coming up in the class later. Those are going to be Gibbs and MH to come up with some sort of sampler to sample these things conditionally. Okay, and so what these methods basically do is first you'll get a conditional distribution based on sigma squared and y, sample beta, then take this beta to the next step, sample sigma squared given beta and y, and then take this number, and it's like a loop, and maybe I shouldn't have chosen n, but like g times. And after that, then you have posteriors for beta given sigma squared and y. These will be your posterior distributions. Okay, so that's what we'll do next.